This last example, you graphed a little bit of higher order polynomials last year. What do you remember about graphing things power x to the 4? Could have a shape something like this, right? Okay. It could have 4 x-intercepts. It could have 0. It could have up to 4, depending on like where you put your axes. Like if my axes were here, I'd have no x-intercepts. If the function was here, I would have 4 x-intercepts. I could make it so that it just had 2 x-intercepts or 3 x-intercepts, or 2 up there. So depending on where these axes are, then you've got different options for how many x-intercepts it has. But because it's a positive x to the 4 graph, one of the things that we learned last year is that any even number acts like a parabola. And positive parabolas start at positive infinity and swoop back down and end at positive infinity. So an x to the 4 will act the same way. But other than that, there's not much information we would have from the past. Okay? You would have been asked to find your y-intercept. It's not hard to find our y-intercept here. Plug 0 in for x. We would know that -3 is a y-intercept. You would have to be able to factor it in order to find out any x-intercepts, or use a quadratic formula. But in this one, it doesn't look like it factors nicely. In fact, it doesn't factor nicely. So all we would have is we know that the shape ends and goes like this, but we really don't know how accurate that graph is from here. But from last year's course, this is about all the information that we would know. We could plug in some more values to get a little bit more sense. But using the techniques we had from last year, we could find the y-intercept. We know the general shape, but that is the extent of it. What the calculus will do is help us find out where these points are. And it will also explain where it's increasing and decreasing. So we'll look at that. So we start by doing the derivative. 4x cubed minus 8x. Make it equal to 0. I'm going to factor, thank you, 16x. I'm going to factor out the 4x, leaving me with x squared minus 4. Oh, that's a nicer number, 16. This factors even further because this is the difference of squares. X plus 2, x minus 2. Someone would think I designed this question, so it worked out nicely. And we get x equals 0, x equals minus 2, and x equals 2 as all the places where our derivative is equal to 0. We have no non-permissible values, but now when we want to find out where things are increasing and decreasing, we have 3 values, which kind of makes sense according to the graph that we thought it would look like based on previous years. Again, we're going to plug things into our derivative to find out where our function is increasing and decreasing. So anytime you want to figure out what the arrows look like on this, you're always going back to this equation, not the original equation. Anytime you want to find out actual points, when we go to graph this, actual points on our graph, well, points on our graph come from our original function. So we're going to do that in a second. But first of all, if you try a number less than -2, like -10, okay, you could plug in -10 into here and solve it. Okay, there's a little bit more mental math involved. I like to use the factored part when I do it, because if I use the factored part and I put in a negative 10, can you see that this is going to be a negative number, this is going to be a negative number, and this is going to be a negative number. And a negative times a negative times a negative will still be negative, so I know this part is going down. If I try a number between negative 2 and 0, like negative 1, this will be negative, this will be positive, and this will be negative. Negative times positive times negative makes a positive. This part will be going up. When I try a number between 0 and 2, like 1, this will be positive, this will be positive, this will be negative. We will get this whole section negative again, going back down. And finally, when I plug something in larger than 2, all of these would be positive. And that section would be going back up. From this graph, we already know this will be a local min, this will be a local maximum, and this will be a local minimum. One of those local minimums or both of those local minimums might be absolute minimums, might be the lowest the graph ever goes. Okay? When we go to plug in values now, well, if I plug in 0, I know that I get 0, 3. I now know that this little red point that I was estimating before actually was right over there. Yes, negative 3. I forgot the negative. Oh, now it looks like a semicolon. Zero, negative 3. And when I plug in 2, now if I want to find these points, 0, negative 3, negative 2 comma something, and 2 comma something, I have to go to my original equation because I'm trying to find points on my original graph. So now I'm going back up to here, plugging in negative 2 and 2. I'm going to get 16 minus 32, negative 16 minus 3, negative 19. This one will also give us negative 19. So as far as my scale goes, negative 2, negative 19, both of those are absolute minimums. That's the lowest it ever goes. And now, from my graph, you know, it goes down, then it increases, then it decreases, then it increases again. And that's my final graph. Much more accurate than it was before. If you wanted to find the last key points on our graph, our x-intercepts, we could find them without a calculator. Okay? I'm going to just rewrite the equation. Our original equation was x to the 4 minus 8x squared minus 3. Okay? Solving for this, it can't be factored. Solving for x to the 4 is not something that you're used to. But if we just do a little substitution, let's let y equal x squared, or some other letter. You always use z. What letter would you like to use? Would you like to use z? Okay. Always use it. It's the last letter of the alphabet. It's got to feel important sometime. Okay, so if we let z equals x squared, can you see that we could rewrite f of x now as z squared minus 8z minus 3. And if you were trying to find your x-intercepts, then you plug in 0 for y, And here you'd say, well, can I factor it? No. And if you can't factor it, use quadratic formula. So our quadratic formula would say negative b plus or minus square root of b squared minus 4 times a times c divided by 2a. Okay, what is that music? But what video has that always at the beginning? Economics videos always have that song at the beginning? Okay. Because I like, yeah, whatever. Okay, back to this. So, plugging this in. Oh, we were using green. We'd have 8 plus or minus square root of 64 plus 12 would be 76 over 2. Does this simplify at all? Can you divide 76 by 4? Yes, 4 times 19. So we'd have z equals 8 plus or minus 2 root 19 over 2, which means that z is 4 plus or minus root 19. But of course, what was z? Z was equal to x squared. And then if you wanted to solve for x, you would have to square root both sides. So when you square root both sides, you have to add a plus or minus. Now, I'm going to write 4 plus or minus root 19 right now, but there's going to be a problem with the 4 minus root 19. And besides the fact that I forgot the root. There's still a problem. It was a bigger problem when it was 4 minus 19, but the problem stayed the same. When I do 4 minus 19, I get negative 15. That's a problem with the square root. When I do 4 minus square root of 19, well, the square root of 19 is a little bit bigger than 4. So that gives us a negative number inside a square root. So that will be a problem, and the only answers will be square root of plus or minus 4 plus square root of 19. And now we could go back and label those on our graph. Again, now this is showing we have really, this would be negative 4 square root of 4 plus 19, and this one comma 0. And this point would be square root of 4 plus root 19 comma 0. So now we have a really, really accurate graph. We know where it's increasing, we know where it's decreasing, we know where its minimums are, where its maximums are, and we even were able to use our previous math to find the x-intercepts.